Hi, this is a talk that we gave at the 37th Chaos Communication Congress. This video version has updated slides. They are denser and more comprehensive, so I encourage you to pause the video if you would like to read a particularly dense slide. Enjoy it.
All right, welcome. Really glad to see you here. I'm Eva. I am a mathematician. I started looking at this project a few months ago. This is Leif. He's been a long-time contributor, and he's somebody who thinks really in depth about these issues and has been for a really long time. And we are here to talk to you about some issues we've faced, maybe overcome, and the general pitfalls in the design of anonymity systems. All right, so let's talk about surveillance, because there's not enough of that around here. We are facing incredibly powerful adversaries, which makes everything super difficult. And there's a probably non-exhaustive list up here. Let's go through it a little bit. So we talk about global adversaries if we think that there is someone who can more or less see connections in the network wherever they are. The problem is, for a lot of the issues that we're facing, that's not even necessary. Like a lot of the time, you could, like your adversary is powerful enough, even if they can just observe two people, and you can still see enough of a pattern to really compromise you. We're looking at adversaries that can compromise parts of the network and perform active attacks on devices that you're trying to use. Willing to make decisions based on partial evidence. I suppose you could take a shot around here every time someone says we kill people based on metadata. But you know, it's important. Like it implies that there's no need for proof. That even if you have sort of a probabilistic bias that something is happening, there are adversaries out there that are willing to pull the trigger. Large computational resources, advanced cryptanalysis. We really have to have as solid crypto as possible. May have quantum computers soon. I've been hearing for 15 years that it's going to be 5 years from now, but you know, we still have to assume that it's possible. And can supplement collected data with rich context of already gathered data on all users, because look around, right? I mean, we have so much context that even if you let go just a little bit of information about your users, that information can be matched to a person. Because Google, because Amazon, because everything that surrounds us, right? All right, so with that, I mean, do we just give up? It's obviously going to be extremely difficult. You don't want to overpromise on anything. You want to be super, super careful. The point is, you really have to shoot for the moon. You have to aim at giving them nothing. Absolutely nothing. No information, no bias, no like statistical inference that you can actually protect. And I mean it. Because even if there is a little bit, just a little bit of bias, if you're watching long enough, you're going to see it. You know, this is one of the most beautiful theorems in mathematics, that if you have a certain probability, if you're repeating a process long enough, then your proportion, your detected probability is going to be as close to it as you want. Right? Which means that, you know, you have Alice and Bob, two users that are talking to each other, and you don't want somebody to know that they're talking to each other. But, you know, the adversary might conclude that if they're actually not talking to each other, ever, then the probability that they will be online at the same time as some p. But if they are instead talking to each other, it might be a little higher. It might be like p prime, right? Even if those are really close. If they're watching long enough, they're going to detect it, right? And this is, in some ways, a problem you cannot get around, right? Because your users are humans. They're not perfectly spherical objects in a vacuum, they're going to have some behaviors that are going to leak, right? Well, the good news is that if you're a really careful user, you can actually help yourself, right? You can make sure that your own behaviors maybe don't give you a certainty of privacy, but they can extend the time that it takes to detect something, which is really the point. All right. So, what's the basic point of an anonymity messaging system, which is what we're really talking about here? We want to enable people to talk to each other and maybe not have that be known. It's a collection of network devices that attempt to relay the messages so that if somebody is just watching the network, they're not, hopefully, going to know who's sending messages to whom. The talk yesterday had a much slicker picture of this type. It's hard to follow that. Here I am with my Dixie. So there are some basic strategies. Something you could do is collect a bunch of messages and then release them either at once or in some other order. You're essentially taking more time to send the message through the network, and that will make sure that your messages, that it's not obvious which message is which. Another strategy that some people use is you make your traffic pattern independent of whether someone is sending a message, right? So you have a packet every so often, and that's not gonna depend on whether like something is a real message or just a decoy message. You can use both. It would be impossible to actually honestly provide privacy without doing either one of these things, right? Without doing both, in fact. Because if you just have a packet passing through the relay at once, like it doesn't matter how many other packets are going through, like you can correlate it, right? Because time is very, very granular. And if you're not at least padding your packets to a standard size, then you can also recognize which one is which, right? So you have like an absolute minimum, like it has to be non-zero on both of those counts. Oh, wow. Okay. So what actually happens when we talk about two packets being mixed in a relay if they're there at the same time, right? And then they come in, they're there at the same time, they leave, possibly in another order, and we are hoping that the perceived probability of the adversary is more or less uniform, right? Because then otherwise, if there is like a big bias towards the actual real matching, then you're not achieving very much. But you have to have some overlap. You have to have a little bit of time. And then we say that the two packets are mixed. But you have to do it smart. Like it has to be a little probabilistic. If every packet is sitting for like the same amount of time, then you can obviously match them, right? Because you know when it's leaving. So that even if there's a bunch that are there at the same time, there's always going to be a probabilistic. Oh, sure. Even if there's a probabilistic component. There's a principle called the anonymity dilemma that you always have to compromise on either latency, so the time it takes for the message to go through, or bandwidth overhead to actually protect against strong adversaries. It's kind of a widely accepted principle. Some people have claimed to prove it. This is a picture from a paper that claims so. I gotta give you a caveat that I haven't verified this formula. And there's some other papers in the genre that don't quite hold up to scrutiny, so I'm going to give you a caveat here, but this is a very useful picture because it has a list of various technologies that try to provide privacy and where they stand against adversaries that can do statistical analysis, right? To correlate senders and receivers. And some of them are more ambitious than others. And basically you have an upper bound of some measure of strong anonymity that is defined in terms of your bandwidth overhead and latency. Okay, so because you have to compromise on either latency or bandwidth overhead, it is basically impossible to have strong anonymity and browse the internet comfortably. Like any service that claims to provide that is overselling, right? Because browsing the internet is not like latency tolerant, and also people expect to have access to high bandwidth. So at some point, if you're like, even if you want to make your traffic constant, like if you're going to have to keep up high levels, that's going to add up very quickly, right? All right. Do you want to take this one?
Yeah. So let's see. To get these sort of properties that we're looking for, we basically need to have applications that are designed to be latency tolerant from the beginning. It's possible, of course, to put arbitrary things over a mixnet, and the Katzenpost software can be deployed in with different network parameters where the latency is low enough that you could actually browse the web over it. However, you won't get the same kind of properties that you get if we have a, say, messaging application which does not reveal when the user is, say, flapping on and offline. So one easy example to think about here is we've got like cover traffic, say, between the user sending loops through the network, and if somebody's observing the user, they have the property of the sender and receiver unobservability. When the user is actually sending and receiving something, their behavior looks the same as when they're not. But if they're downloading a file through it, if you have like, if you're downloading a file through this, and say you have something like equivalent to a Tor exit node, and you're downloading a file, and your neighbor's microwave turns on, and now your Wi-Fi drops out for a minute. The drop in that bandwidth, the fact that you went offline and home for a minute, is going to correlate with the download graph on the web server that you were downloading a file from. The basic, like an HTTP download forces interactivity in the form of ACKs. Of course, the exit node could be sending ACKs and buffering the file arbitrarily so that that's not visible to the web server and is only visible to the exit node. But still, if it's HTTPS end-to-end, there could be a key renegotiation. Basically, you can't download a file in a latency-tolerant way. You need a downloading service. So you can have like a file downloading service that fetches the file. And there's a lot of mixnet native applications that could be built that are latency tolerant like this. The one that we have right now is a very simple chat client, which we'll talk about a little. Yeah.
Right. Oh, this actually works.
We're a little short on time, so I'm going to cut that slide there.
Alright, so there's a popular mixnet design that a bunch of systems are trying to build on. It's called Lupix, and it was released in 2017. And it has 3 fundamental building blocks. So I told you that in order to actually mix 2 packets, there has to be a probabilistic component, and they have to sit together for a while. So the way this is done here is they sample the delays from the exponential probability, which is actually a really good idea. This means that it's memoryless, and the definition of that is it doesn't matter how long you've been sitting in the node, like what's ahead of you, the time distribution looks exactly the same. So if you have 2 packets that are in the node, then they have exactly the same time distribution going forward, even if one of them has been sitting for much longer. So from the point of view of somebody who's on the outside, it is equally likely that the next one is either one of those 2 at all times. So this is really good. And this shows up first in a 98 paper called Stop and Go, or, well, it has a longer name. Then the second fundamental sort of characteristic of this model is that some of the packets are sent by various network devices and are supposed to come back to them, and then that device can take stock of the functioning of the network. Basically, if something's not working, then the packet's not coming back. So you can kind of figure out that someone's messing with your network or just not working efficiently. And then 3, between you, the user, and the mix nodes, the servers that are trying to mix the packets, there's a service provider that just does a lot of the work for you. It eases the resource burden on you because it actually decrypts a bunch of things and mostly just sends you the legitimate messages. And you can receive messages even if you're not online thanks to them because they're going to keep it. These are also a big headache because it's a huge point of failure. Like if someone is after a specific person, this is the point they're going to go after. So there's actually a lot that can go wrong here. Okay, so we got these 3 fundamental building blocks. And, okay, so unfortunately in putting those together, some mistakes were made, okay? And I would like to see a show of hands, if I may, if you've heard the words Poisson mix. Okay, a few? All right, fewer than I expected, but okay. The paper that introduces this model bases their analysis and proofs and statements on the belief that the node itself behaves like a Poisson process when you sort of look top down at it firing messages. And this is admittedly, this is a mistake carried through from that 1998 paper. But that one doesn't quite lean into it as much, like not as much of the paper depends on it. Both papers cite the fact that, if you add together Poisson processes, the result is a Poisson process. Well, not the way they're doing it, though. Like you have to have like steady collection of the processes. If you sort of keep changing how many you're adding, like, no. And I suppose I could... All right, so maybe a short time to think about that. Let's see, there's a picture. Okay, so if you have your time axis, there are some things that happen. They happen boom, boom, boom with some probability, and you can model a bunch of things that way. Particle decay, for one thing, right? If these gaps between the times the event happens are sampled from an exponential distribution with a constant parameter, then this is a Poisson process. And it's counted according to the Poisson distribution. Now, this can be explained pretty easily with a coin toss because most people... Yeah? All right, most things in probability are secretly about the coin toss. Yeah, is that good? All right. So if you're tossing a coin repeatedly, the probability, the time to first success is going to be like, you want tails, for example, right? And it's probability 50%. So you have 50% that you get tails straight away. All right. Then you have probability 25% that you get heads and then you get tails. Then you have probability 1/8 that you get heads twice and then 1 tails, right? So that decays exponentially. And secretly, if you kind of decrease your time increments and adjust your probability of success so that your expected time of success is the same, then the limit of that process on a continuous time, because you're decreasing your time increments, is a Poisson process, right? So what you're seeing here is you can think of as like rolling dice. Rolling dice repeatedly, same dice, same chance of success. But here we're changing the dice, right? So a lot of the theorems in the paper are actually don't hold up. So this is how this process, right? Like you're tossing it, say once a second, twice a second, but with smaller probability of success. 4 times a second, and so on, it starts fitting into an exponential decay. You can also make a node actually behave like a Poisson process, because right now the probability of success is going to change depending on how many messages are in the node or how many users are in the system. The this behavior is actually not memoryless, right? But you can make it so, right? You can have the node have like an overarching distribution, like you decide if you fire a message or not, right? And then you can fire those messages however you want. So you could actually have it as a Poisson process without achieving any mixing. You can put your messages in the queue and then release them in order, but according to a time distribution that corresponds to exponential decay. All right, so there's actually other problems with using that word because it's misleading. What you're actually implementing is the exponential distribution, right? So some poor developer implementing this model might accidentally sample from a Poisson process, and that's a problem. So I'm going to propose that we call it memoryless mixing instead. Don't call it a memoryless mix, because it's not actually memoryless. But memoryless mixing would be correct. So I'm going to propose that we change that name. Okay, do you want to take this one?
Yeah, so one of the things that we have done on the Katzenpost project in the last year or two is added various post-quantum primitives at several different parts of the system. I guess actually I'm going to go through this list in the opposite order. Sphinx signatures, there's two different things called Sphinx in the Katzenpost project now. The new one is the STHINCS signatures, which is a hash-based signature scheme. So we signed the consensus document with that, along with ED 25519 signature. So it's a hybrid scheme, just in case Sphinx somehow doesn't work out. They're kind of big. They're, I think, 49 kilobytes or something. Maybe I'm wrong. Yeah, I think that's the size. But we only distribute these every so often, so it seems to work. Our double ratchet is now a hybrid double ratchet using the C-side non-interactive key exchange primitive, and also in a hybrid construction along with X25519. The noise link layer encryption is using Kyber. We're using a chem combiner that takes a chem made out of X25519 and the Kyber chem and combines them together. And so our link encryption is now post-quantum. Also, the Sphinx packet format is the hard part to make post-quantum. We have two different ways to do it. And all of our crypto primitives are pretty pluggable now. And in Sphinx, on our current sort of test network, we're not actually using one of the two post-quantum Sphinx things we have because they both have some trade-offs. One is a C-side based Sphinx modification that is nice, but a bit slow. So it would be useful for a mixnet that doesn't have a high volume of traffic, which also means that your latencies need to be much higher. But if you wanted to make like a remailer, kind of like an old-fashioned mixnet, it was very slow, then the C-side Sphinx packet format is there for that. We also have a thing that one of our main developers, David Stainton, is called Chem Sphinx, which is like the Sphinx packet format, but actually using a chem. So you lose the killer feature of the Sphinx packet format, which is compactness. So these envelopes are quite large, which means it's not really useful for sending small packets so much because the overhead would be too much. So currently we're actually using the Sphinx packet format without any post-quantum encryption, but because it's wrapped at least in the post-quantum link encryption, the only people that can attack it are attackers that have compromised one of the nodes. So like the passive internet adversary can't see the Sphinx packet to attack it. And yeah, that's the summary of the post-quantum additions to Katzenpost recently. Yeah, so for making a latency-tolerant applications, where we sort of started with and where we're still sort of at is that we have this messaging application has a spool provider. So the mixnet service is a spool that you write to and read from, and it doesn't know where the user is, but it does know that this spool has existed for this long, and it gets read at these times, so maybe they could guess what time zone you're in, knows how often you receive messages, how often you check them. It just doesn't know where you are, because it's on the other side of the mixnet. We would really like to not have that metadata, because all of that information that the spool provider knows could be useful if you successfully attack the mixnet and find out where the user is. So we're working on a design of a thing that is kind of like a DHT, where the sender and receiver can construct a chain of single-use mailboxes that you write. You know where I'm going to write the next message to you, and you're checking that one, and as you receive a message there, you never check it again. So from the perspective of the storage providers, there's much less linking of user activity. So each message is not linked on the remote side where the messages are stored.
All right.
There's a test network for Katzenpost. This is something that we we're hoping to have a website that actually describes this network in time for Congress, but we do not still. It's a network that we're not looking for volunteers to help run it. It's a handful of volunteers, and we don't really need more people for the small number of test users we have. I mean, you can use the network today. We're not distributing binaries of the chat client, but if you build it yourself from github.com/katzenpost/katzen is the name of the chat client, it will use the namenlos network, which is running with cover traffic that it's sending and receiving is somewhere around 20 kilobytes a second. So if you run this on your phone, it builds for Android as well as desktop, it will use a lot of data. So with the current network parameters. We've also set up networks using very different network parameters, but the one that we have right now that you use with Katzen, we're calling namenlos, and yeah, it's about 20K a second of cover traffic, and which is the same as when you're actually using it. So the traffic profile is continuous.
All right. Okay, so here are the basic takeaways from this talk. It's super hard, and we're just really determined to not oversell. Which is, you could say it's holding the project back, but I mean, come on. It's necessary though, right? We need it. Have you seen the world? At some point, like every so often shit hits the fan even more. At some point we're going to be desperate for something that actually guarantees things. So we're trying. Do you have anything to add?
It's a hard problem. We expected to be further along with the project by now, and we made a lot of progress in the last year, but we still are not at a point where we are inviting everybody to start using this as a daily messaging. You can actually use it today and chat over it.
And it is probably free software, right?
Yeah.
So that's a plus.
Yeah, it's a framework for building mixnets. It's the namenlos network is just one instantiation of it, and there's a number of other people that are working on other ways of deploying it that I won't get into in this talk because I'm not involved in so much. But it's a useful framework for experimenting with. Different ways of
and some applications lend themselves to this format more easily than others, like messages rather than browsing the internet and so on. So those applications that Leif is talking about are all sorts of more appropriate for a latency tolerant system.
Yeah.
All right, thank you so much. Literally 5 minutes if anyone has any questions. Yeah?
We'll also take questions after, of course.
Yeah. We'll be outside.
What about text-based browsing? Maybe you just want to list something in the...
About what?
Text-based browsing? Actually, you're asking the right person.
I've got a long story about how mixnets are useful for really very private web browsing, and we can talk outside about that. But it's very
You're
different
not going to be streaming new movies, though. All right.
Let's go.